Hello, good morning everyone. Nice to see you all again. Right. So today we will go into the third sessions of this course, and we will focus more on the electro-pneumatic system. Okay, so the title is electro-pneumatic slash hydraulic system. Okay, but we will focus more on the pneumatic systems in the discussions later on. Okay, uh, since both of them are quite similar, right? So once you understand about the pneumatic, then you should be able to deal with the hydraulic. So before we move on, right, just a quick review, right, of what we have discussed previously on the components for industrial automations. Okay, we have different types of hardware such as sensors, we have the actuators, we have the the computing part, and so on, right? So all these things can be actually grouped. Okay, all these automations can be grouped into different levels of I would say authority, or how the data should flow, right? It depends on how large you want to make for your automations, right? But then it would always start from the device level, the very low level, okay, where it only includes the actuators, sensors, and the hardware itself, okay, where they communicate among all these components. Then at this level, after that, okay, then you may want to have a machine level, okay, where these machine levels now including performing the tasks in a correct order within a same machines. Okay, so you may press in the machine saying that to do part A, right, or task A. Okay, so this task A at the machine level will now start to instruct, okay, what to do, what is the order within the machines. Okay, then slowly when it go at the higher level, okay, then the informations flow to what we call cell, or maybe a system where it may combine several machines or stations. Okay, they will start to coordinate among themselves, okay, whether the object have been sent out to the next stations, whether the next station have received it or not. Okay, so in order to process, okay, in a high level. So all this data will always go back and forth, as you can see in the flow, that the data will flow from the lowest. Okay, they will tell whether it has done a certain job, right? So the machines level will know, okay, task, this certain job have been done. Okay, so next order of the task or job, right? So they will continue to flow, but after that they will also continue to communicate with other machines in the same cell or the system, right? Then further on top of them, there would be a plant level, okay, which would be the factory type of level, where you may not only communicate within one cell or system, but you are now commenting with different level of automation within the factory or the plant. Okay, so this could be a high level of maybe a computer integrated manufacturing type, okay, where it includes the functions of ordering, processing. Okay, so the purchasing department will send an order saying that, okay, I would like to have this automation, this product, okay, to be fabricated, okay, and how it would affect the quantity in the inventory and so on. So this would be in the plant level, right? Then also in the plant level, there is a quality control. So if for example, here we have one lecturer, okay, so he actually do some kind of industrial automations programming of the system itself, where they do sell this software or automation software, okay, I would say automation software to a company doing glass. Okay, so glass panel usually have a certain type of I would say size. Okay, when the glass panel come in, okay, they will have a certain size, right? So the productions itself now, when the factories doing the order, so they will say, okay, this customer want size A, size B, size C. Okay, so this big large panel now is now being planned. Okay, so the software itself have the algorithm, okay, to actually calculate how to save the space, okay, so that it maximize the total area of the original glass panel, okay, in order to produce a smaller part. Okay, let's say window panel, okay, which is as size A. Okay, so maybe a customer orders 100 piece of it. Okay, so this machine will now start to calculate all these things at the plant level, and they will send all this instruction to the machines, okay, at the factories to do the cutting, okay, on their own, right? So this is the level of things. Then at the most high level is the enterprise level, which mostly deal with the business automations, okay, where they require the data for them to plan, okay, to market, okay, and so on, right? So this also include the design part, okay, how you can maximize the size of of your raw material, okay. Right. So back to this sessions, okay. So this session is about pneumatic and hydraulic system, okay. In general, we would group them as what we call a fluid power system, okay. So these fluid powers will always used to transmit and control an energy through the applications of pressurized fluid, okay. So we use a pressure to push or to transmit the energy through the fluid itself, okay. So it could be in the form of hydraulic, okay, which we usually use oil, okay, but we can also use water, as well as pneumatic, which will involve the usage of a compressed air or inert gas. So the functions of these fluid power systems, okay, in general, would be to provide the force and motions, okay. The main part is the desired force and the motions, okay, to various mechanisms, and those mechanisms usually are very simple, okay. It could be in the form of push or pull, or rotates, okay, rotates at a certain speed, so we could call it regulate or drive, right? So these are the simple tasks, okay, that we usually use in industrial automations, okay, to perform various complex tasks itself, okay. So it could be a very complicated or difficult task, okay, but we would always want to simplify the task itself by breaking them into a simpler task, okay. Let's say if we want to pick something, okay, if we use our hand to pick certain things, okay, it could be very easy because we have multi degree of freedoms, okay, for our hand, okay, as well as we have leg. But then in order for us to perform a certain task, okay, to replace a human, what we can do is we simplify the task into just a linear or rotations, right? So this is how we could do the simplifications, okay, in order to achieve the desired automations, right? So the advantages of using the fluid power systems could be includes we eliminates the needs of power gain, okay, as we don't really needs the gear, okay, to amplify the power, right? As well as since there are less moving part inside, so there will be less wear and tear. That's why this kind of fluid power systems are are preferred in industrial automations because it can last very long, right? So if required, then they just change a certain part, okay, and the maintenance are also quite easy. Okay, we just have to change the oil from time to time, okay, or maybe the o-ring and so on, okay. uh, Others advantages includes constant force and torque, right, that it can provide, the flexibility of using pipes and hose, okay, so that your actuators actually can be located at various part, okay, and you don't need a gear at the specific locations to actually transmit all this power. You just need a pipe to connect them to the reservoir of oil or the air compressor, okay. At the same time, they also produce large forces, okay, with very minimum or small pressure loss, okay, throughout the transmissions, and it is always safe in the dangerous environment, okay, especially the pneumatic one. You just release the air, right, or you can also release the inert gas, okay, so it will be less risky, okay, in a dangerous or hazardous environment, okay. For sure, there are also disadvantages, like if you really want a very precise control, okay, where it's involved a dirty environment, okay, dust or maybe others how would I say, debris, all right, that comes into the machines, okay, then this will make it difficult for you to actually maintain the precisions, okay. They may not mean for very precise machinings, okay, not exact very precise one, right, but we can still maintain a certain level. That's why tolerance of the manufacturing's part is very important, okay, to identify how much sensors and the accuracy of precisions are required, okay. So when high precision is required, most of the time the pneumatic may not be a good choice, right. Then also they need to be protected against rust, corrosions, and oil deteriorations, okay. So that's why you need to keep changing the oil. Here is the comparisons between the pneumatic and hydraulic. Basically, pneumatic is just using the air, right, and hydraulic using so-called non-compressible fluid, right, like water and oil, right. So for sure, because of that, they have a higher pressure, okay. Then in terms of actuating force, the hydraulic will give us or provide us with a higher load, but then when it comes to the cost of the component or the elements of it, then the pneumatic usually costs less, okay, as compared to the hydraulic, maybe in the form of 5 to 10 times cheaper, right. Then the advantages in the pneumatic is that it's much cleaner, right. So the transmissions line is just clean, where you just exhaust the air to the atmosphere if you want, right. So this would save us a lot of pipings and so on, right. And those would also include cheaper type of or lower cost of tubing and so on, okay. We don't need expensive fitting, okay, in order for us to work in the very high pressures, okay. But then in the expense of that, the hydraulic will have a higher stability because it's not compressible. That's why the positions or the movement is more stable, okay. Whereas the pneumatic, when we give additional load to it, then it will behave differently because we can always compress the air, right? And for sure, because of that as well, the hydraulic are easy to control, okay, in terms of the speed. Okay. Here is the comparisons between the pneumatic and hydraulic in terms of the advantages and disadvantages. Okay, the main advantages of the pneumatic for sure is clean and fast. Okay, that is the main point, right? You don't need to really depends on the pump, okay, to pump it, because the air move very fast. Okay, you just compress it and you just release. Okay, and it's also so-called explosion proof, okay, because of the usage of the inert gas or maybe the air, which may not react to most of the explosions or fire, right, hazards. They are also easier to design and implement, more reliable, okay, with lesser moving parts or maybe fittings, okay, and also easier to install and maintain, right? But then hydraulic for sure, if we really want a large force, okay, and precise tolerance, okay, then we would now choose a hydraulic, okay, instead of a pneumatic, right? Also, if we desire a high power output or high power output, then we also would want a hydraulic. And because of we are using a fluid, okay, then it's have the advantages of it can be transmitted through a very long distance, okay, without much losses, okay, as compared to the air, since this is very how should I say, compressible, okay. So if it is at a very long distance, then your connection or network of the pipes now have to be upgraded, okay, so that it can withstand the pressure that you intend to compress, okay, so that it can be transmit to the other place, okay, of how I say, of the machines or the device, okay, of your pneumatic system, okay. For sure, it's still safe and reliable, and the main difference is that pneumatic are usually smoother and quiet, okay, whereas for the hydraulic are usually smooth and quiet, whereas for the pneumatic they are a bit noisy, right? So there will be a lot of noise pollutions where the valve will release the air and so on. So you will immediately recognize that there is a lot of noise pollutions when we use a pneumatic, okay, especially when you have a air compressor within the same environment. So the air compressor will keep compressing the air, okay, then your pneumatic cylinders and so on will keep releasing the valve, okay, so you will hear the sound of the releasing valve and so on, right? Okay, so now come to the pneumatic system itself. The basic components or the setup are generally like this, okay. You may want to remove certain things, okay, it's up to you, right? So generally it may comprise of the main compressor, okay. So you must have a compressor, whether it's located in the same room, next room, upper floor, lower floor, or whatever it is, okay. So it will compress through maybe an engine or an electric motor, right? So this will keep rotating, okay, when it is being activated. So there is a pressure gauge that we can see what is the pressure inside, okay. So also we have a pressure switch, okay, to release, okay, and also to control. So whenever the pressure inside the tank exceeds certain pressure, then you will start to release, okay, or you can manually release it if you want, right? And also it will gauge, okay, to the desired pressure that you need. Okay, so when the pressure inside drop, okay, then it will kick in again the electric motors to compress again. Okay, so this is a continuous process. Okay, bottom there we have a drain usually, right, to drain certain oil or water within inside the the reservoir itself. Okay, then when it come through the system, pneumatic system itself, then we will have different type of filters. Okay, so all these filters actually mainly to remove all the water, okay, as well as the dirt or debris, okay, in the air that we use to compress, right? So when we compress, there is a the moisture inside the air, right, or in the gas itself that we may want to remove it, okay, in order for us to prolong the operations of our cylinders, okay, the actuator itself, right? So you may go through the air dryer, okay, to reduce the moisture content. Then after that we will have this so-called after filter. So this after filter is used to protect the equipment from the dust, etc., okay, by having a porous media, okay, to filter them out. Okay, then also we have a air service unit, okay, such as filters, other filters, regulators, lubricants, and so on, okay, that would clean and lubricates the air, okay, before we deliver to our pneumatic system. Okay, so in our discussions, in these sessions we will concentrate more on this part, right, the compress, the valve, and the actuator. Okay, whereas the rest of this we just assume it is already there. Okay, there is a backbone of this infrastructure that deliver the compressed air that we need. Okay, then the rest would be how we can deal with this part, right? Similar to the pneumatic system, we have this hydraulic system. Okay, the only difference is that we don't need to keep producing the compressed air. Okay, but what we need is we need a pump, okay, to deliver the oil or the incompressible fluid, okay, to our system. Okay, so we have a pumps, okay, to pump in the fluid to our system, and usually this fluid will go back to our reservoir. So in a sense it is I would say less waste, okay, but lesser waste, okay, whereas in pneumatic we usually just exhaust it to the atmosphere, okay, unless we have a series of so-called systems, okay, where they would release a lot of air, okay, then that part, then we may want to reconnect them to a lower pressure tank, okay, to save the power of keeping compressing the air from the atmospheric pressure to the high pressure that you want. Okay, so when we release it to maybe a lower pressure of tank, then it will help in or to reduce the energy required to compress to the higher pressure. Okay, generally in these hydraulic systems, we have filters, a check valve, and so on. Okay, so this check valve to ensure that the flow is only in one single direction. Okay, we don't want the fluid to flow back okay. Then after going through our valve and equipments, then we want also to filter them out, okay, to clean the air, because they may have foreign particles, okay, due to the movement the of the valve or of the pistons itself, okay, where you have a debris, okay, coming back, right? So you intend to filter them out. So there are two ways of filtering, okay. One is to use a full flow filter, okay, where we will filter 100% of the fluids passing through the filters, okay. So whatever it comes, it will go through that 100% of the filter, okay. We call it a full flow filter. Another part would be we call it as a proportional flow filter, where we only extract a certain portions of the flow, okay, to filter it out, okay. The idea is that the amount of debris may not be that high, okay, that we and this pumping will continuous, right? So in that sense, we have this ideas of only filter a certain part of it, okay, a certain amount of it, okay, by using maybe a venturi type of truck, okay. So due to the constructions of the venturi, okay, so at the smaller diameter of this venturi truck, okay, then you will have a lower pressure and the higher pressure difference, okay. So eventually, because of that, the oil, certain part of the oil will now move to this filter, okay, through this venturi truck, right, toward and being filtered out, okay, on that small part, right. So it will continuously to flow, okay, and it will continuously taking small portions of it to be filtered, right. So it has the advantages of reducing the pressure drop, okay, caused by this filter, okay. If you want to filter the whole amount of oil, then the pressure drop across this filter will be very high, okay. The electro-pneumatic component, when we see the words electro, okay, it would always involve the control of the pneumatic systems using electric, alright. So that is the idea of using the electro pneumatic, okay, especially when in this highly digital environments, okay. Nowadays, electro-pneumatic or electro-hydraulics systems are becoming more common, okay. Only thing is the cost of using the electro are usually greater, right, due to the usage of the solenoids, okay, within the component itself, okay. So the components are very straightforward, okay. We use the source of the compressed air or the pressurized air itself, okay, either through the compressor, okay, piston type or turbine type, okay. Then we have a distributions of the pressurized air that may involve a piping from plastic to copper or steels, right. The selections of the pipe diameters may involve the requirement of the amount of air that you need, okay. We call it volumetric flow of the pressurized air itself, okay, because every single cylinders or of the actuator, okay, the bigger it is, you need more volume of it, okay, to be delivered in order for us to perform that kind of actuations, okay. So that is the amount, the volumetric flow that is required, okay, at a certain instance or time, okay. Then also the length of pipe, the pressures, okay, and the most important part, okay, within this distribution should be the allowable pressure drop, okay, because you, in order to operate that particular piston itself, okay, you may want the pressure to be operated at certain level. Okay, if you are connecting to through a piping which pressure drop is high, then at the end of, or when it reach to the device or the piston itself, then the pressure may not be high enough to operate as what you intend to. Okay, so maybe it will still compress. Okay, it will just move at the slower speed, and at the end it may not reach to the end. Okay, or touching the limit switch, okay, as intended, right? Then for sure the moving part would be the pneumatic device or actuator. It can be in the form of single acting or a double acting. Single acting type usually have a spring. Okay, you just need to input it. Okay, and it would move in one direction. Okay, single acting. And the control of the other part would be you just remove the source, then you will come back. Okay, due to the actions of the spring. Okay, so you just can control the single actions. Okay, then you return by itself. Okay, all these controls of the directions of the flow, we would use a control valve. All right, now come to the selections of the pipe diameter. Okay, to deliver the compressed or pressurized air from your source to your desired valve or system, right? So these selections of pipe diameters are usually very generic, I would say, and it applies the same concept of frictions in the pipe that you have learned in fluid mechanics, I believe, right? For sure. And usually in the industry they just use the term what we call as equivalent length, okay, to estimate the pressure drop across the pipes, right? And we don't actually do a very intense, or I would say formula based calculations. Okay, so instead of that we just mainly based on a chart, right? That would help the designer to actually design much faster, okay, and less error. Okay, less error because when we deal with formula, there is high chance of we press the wrong numbers, we multiply wrongly, and so on. Those are the common mistakes. Okay, not only within students, but engineers or whatever, right? So that's why in the practical side we intend to use all these figures, okay, that are fixed, okay, and we try to reduce all this human error. Okay, so here we have these examples extract from the text, okay, where we intend to calculate the diameter for a pressurized air distribution pipe. Okay, so this factory needs will have a consumption of 800 meter cube per hours of compressed or pressurized air, and the distribution pipe will have a length of 300 meter with 6 T joint, 5 90-degree curve, right, and one two-way valve, right? So for these applications, the allowable pressure drop would be only 0.04 bar, okay, while the operation should be at 9 bar, right? So there is the requirement of the pressure, okay, in the system, right? So you will have you just list it down, the volumetric flow rate, okay, the pipe length, okay, the number of T, and so on. So what we do in this equivalent length is that we would convert all these fittings, okay, or connectors into the equivalent length, okay, equals to our pipe length, okay, before we do the calculations of the pressure drop, right? So if you use the fluid mechanics book, then it would be you may use a Moody chart and so on to calculate what is the friction and pressure drop across the pipes and so on, right? So here we have this we call it nomogram, right? So nomogram is just the ruler's type of chart, okay, that helps us to visualize or to select faster, okay. Even if you are working in the, I would say, HVAC, okay, heating, ventilations, okay, and air conditioning. When we select the size of the duct, okay, ducting within the air conditioners system itself, we also have the chart we call ductilator, okay, something similar to this but in the circular form, right? So it can be in the form of circular or in this form of linear form, right, of rulers, okay. So how this monogram being used, okay, no formulas are required, okay, we just have to use rulers, right? So we can see that the first vertical line represent the length of the pipe, the second represent the airflow, okay, that we require, okay. So we know that from our previous statement, we have 300 meter of pipe length, then the airflow is about 800, okay. So we just take these 2 points and draw a straight line, okay, then it will intersect with this axis A, right? Then the second task would be, we have a desired system pressure, okay, which is 9 bar, right, our operating pressure. Then another part would be the pressure drop, okay, allowable pressure drop, which would be 0.04, right, 0.04. So this point should be up here, right, 0.04. Then again connect them with a straight line, right? So assuming this one is correct, I think they have some descriptions, yeah, maybe I make it wrong, okay. So this could be 0.05, okay. So just draw a straight line, then you will intersect with this axis number 2, right? So we have these two intersections of point. So what we need to do now is that using these 2 points, we draw a straight line, okay. So this straight line will now intersect with 1 point over here, okay, and this tells us what is the pipe diameter we need to use, okay. So eventually we get this around 50, okay, around 90 millimeter, okay, of pipe, okay, that would be able for us to meet all these conditions, right? So it's very straightforward, no equations, okay, and very clear, right? Yeah, okay. So from this chart also, if we intend to do the reverse part, okay, let's say we have a existing system, okay, we have an existing systems, we know the pipe diameters, okay. Then if the systems now change, right, let's say the airflow volume change, okay, we want to increase the volume of usage, okay, then from there also we can estimate what would be the pressure drop or the system pressure from that, okay. We just have this, when this one increase, then we just redraw the line over here, okay, but the pipe diameter never change, so this point connect to this point, so we have this point. So from this point onwards, we would now able to see, in order to maintain a certain pressure, okay, so what will be the pressure drop we expect and so on, right? So we can always reverse, okay, as long as that three straight line that we connect are connecting to the right point, right? Then also, since we have fittings, right, we would want to represent all these fittings into an equivalent length, right? So we refer to another chart, all right, that would estimate or tells us what would it be, right? So since we have selected the 90 millimeter pipe diameter, so all these fittings would now applies a 90 millimeter diameters, okay, and from that onwards we just check, okay, two-way valve, okay, so it would be estimated around 32 meter, of equivalent length, okay, multiply by 1 unit, okay, so we have 32 and so on. So you just extract all this estimated value, okay, of equivalent length, okay, so you get this number, and from these examples we would require to add an additional of 101 meter of equivalent length, okay. So the overall length after going through all this fitting from the compressor, okay, to the machines or the valve or the piston itself, okay, let's say, then the overall length would be estimated as 401, okay. So this 401 is different from the 300 that we have selected previously, right? Okay, previously we used 300, okay, but in actual the overall length is 401. So what we need to do now is do the iterations. So we estimate 401, now we put it back, okay, we just change or update the pipe overall length to 401, okay, repeat, okay, 401, we update it, right, then intersect, okay, since the pressure drop and the system pressure remain unchanged, so we will update it, and we will see that the new pipe diameter that we should select is around 96, okay, 96, okay, but then no, I would say no pipe are actually manufactured at any given size or diameter, okay, so you have to choose the nearest diameter, okay, that's available for you, okay, maybe not 96, maybe 100 millimeter, okay, that you have, okay. So from there onwards, again you reiterate, okay, whether it is acceptable or not, if we are using 100, or instead of that, whether it is a good idea to keep maintaining at the 90 or the nearest one, right? So that is the idea of iterations, okay. So we will always want to start with something, right, then we calculate or estimate, then we further updates, okay, with new informations, and continue with the looping, okay, of your iterations during the design of your pneumatic system. Okay, so far any questions, okay, before we proceed onwards? Okay, if no questions, then we will continue, okay. Okay, so far no response yet, okay, maybe there is some delay, so we will address that in the later sessions, right, the Q&A sessions. Why moisture need to be avoided in pneumatic system? Is there negative side? Yes, okay. So what happens is that when the pneumatic piston, let's say the piston, okay, this is the pneumatic piston. So if the moisture is not being removed, so eventually all this moisture will now enter into our cylinder, and all this water will now get accumulate somewhere here, okay. So one thing is it will create rush inside internally, and second thing is that now because water is highly incompressible, so after certain operations, okay, now this gap will now fill with water, okay, you cannot remove it, okay. It will be a much difficult task for you to actually dismantle the cylinders as itself, okay. So the cost of maintenance will become high, right. So that's why we intend to avoid water getting into it, okay, or else it will stuck inside, and this piston will later on cannot return to the position that it intend to, okay, as well as it will create corrosions internally, right. I hope that would answer your questions, right. So for pneumatic, it's very important to remove all this dust, okay. It will stuck inside the cylinder, okay. Whereas if for a hydraulic part, then the fluid keep going in and out. That's why after it goes in and out, you can see that there is a filter to filter out all the dirts, okay, due to the movement or the abrasion wear, okay, internally. Right, then we move on to this pneumatic cylinder. We can see that there are generally two main type of cylinder. We call it single acting and a double acting. As I've mentioned previously, the single acting will usually have a spring, okay, to return it to the original positions, okay. So you may want to push it in, okay, push it in from one side, so it will extrude forward, right? Then when you remove this air, then it will return by the actions of the spring, okay. So in the symbol form, we may draw in this way, alright. So it's either return to this part or always extruded, okay. When we pump in the pressurized air, then only it's moving back inside, right? Then for a double acting cylinder, in this way, we don't actually need the spring, because we are now controlling the movement of this cylinder by putting two different different pressure of air, okay, into these two pots, okay. So you may put a higher pressure over here, so this one will move to the other side, okay. When we put a higher pressure on the other side, then it will return back, okay. So this is a double acting cylinder, right? So that's why in the symbol you will see two pots, okay, two pots in here, okay. Whereas for a single acting, usually we only have one pot and there is a spring inside it. So other type of pneumatic cylinders, okay, that we have includes adjustable cushions, okay. We have two extruded pistons, okay, so that it will operate on both sides, alright. Then also there are non-rotating rod cylinder, okay. Since this is a cylinder, okay, you can still rotate it somehow, okay, but certain applications you may not want it to be rotatable, okay. It must be fixed, alright. Then in that case, you may have a twin rod, okay, double rod, okay, to prevent the rotations of it, right. Then also we have a tandem cylinder, okay, one after the other, right, so that we can control this one and we can control the other one, right. So eventually there is advantages and disadvantages, okay. Somehow it may act like a valve as well. So when this extruded, okay, and when another one is extruded, so this one may not able to come back, alright, and so on. So there is different functions that we may want to apply it, right? Or maybe we want this to control one part, okay, and this one is being controlled by the other, so it's a combination of cylinders, okay. Other possibility of usage, this it would be the power required, okay. So you may want a certain force, okay, so that you may need two rods, okay, to push it over, right. Then also there are others like position cylinders, okay, that can become in a half length and full length, okay. So you may, because the positions of these cylinders, especially in pneumatic, you may not able to control the positions, okay. So it's either extrude fully or come back, right. So in that sense, you may want to control whether you want to extrude half of it, okay. So if you want to extrude only half of it, then you just activate this one. So this front this back end one will push and this will extrude only half, right. If you want a full length of it, then we just activate the second part of these cylinders, okay, and it will extrude to the full length. So this is how we can control the positions of the cylinders, okay, through the usage of this multiple positions cylinders, right? Then also for a rotational type, you may have a gearing inside, but the operation is still remain very similar. Okay, we just use the pressurized air to actually move this maybe pinion, right? Okay, in order to create the rotational movement. Okay, it's just the transformations of motion from translation to a rotations. Here is a simple again calculations on identifying what is the force, okay, being exerted by the cylinder itself. Okay, the idea is very straightforward. Okay, we have force equals to area multiplied by the pressure. So we have the pressure, okay, we have the area, right? So we have the pressure and the area, right? So from there we would know what is the force being produced by this cylinder itself, right? So again, for a single acting cylinder is very straightforward. Okay, the area is only on one side, but for a double acting cylinder, okay, the retracting part of the cylinders you have a so-called slightly higher force, I would say, because of the reduce of the area, right? So you can see the acting area is getting reduced due to the diameter of the rod itself. Okay, so you can always check all these things. Okay, and for sure the actual force being exerted, we have to also minus the frictions and the spring if there is. Okay, and that roughly take into account of 5 to 20%. So you can just estimate roughly what is the force that we can produce by using that particular pistons, right? So it's very straightforward. The power being delivered mainly depends on the pressure that you supply, right? So in order to select the proper cylinders, you must first know what is the force required, okay, by your system, okay, in order for you to complete the task. Okay, then also second thing would be whether your cylinder itself can sustain that amount of pressure. Okay, you may want a certain pressure in order for you to accomplish a certain force. Okay, but then the constructions of the piston or the cylinder itself may not be able to withstand that pressure, right, because of the size and so on, right? So that would be the selections part of your pistons. Most of the manufacturer will have specifications saying that is the allowable maximum pressure, operating pressure, right? That will helps you to select, right, or to limit your selections. Then also the length of the pistons and the speed, okay, of the translations, okay, that would be as a functions of your manufactured cylinder. They will tells you roughly how it would behave, okay, normally. So generally the speeds of the cylinders are quite high. Okay, it can range from 0.1 to 1.5 meter per second, okay, which is very high, right? Then in order to control the directions of the flow, okay, since we have the single acting and the double acting, then we may want to control where the pressurized air should flow in, okay, which port it should go in, okay, and when it should go in, right? So all this require a control device, okay, and we would now use this so-called a valve, okay, to control the directions of the flow, right? As well as we can apply a control signal like a start, a stop, or to regulate the pressure or the volume. Also all this can be done by a valve, okay, by selecting a proper type of valve. Then you can do all these required functions, either to control the flow directions or to apply a signal like when the pressure reach a certain level, okay, then it will activate, okay. That would be like a check valve, okay. So a certain pressure have reached, okay, what it should do, right. Then also to regulate the pressure, for sure the check valve will release and or close the opening of the release itself, okay, in order to control the pressure within it, right. In these sessions we would mainly concentrate on this directional valve, okay, because this is the main part where we would want to control the directions of the flow, okay, in order for us to actually design and operate the desired, or to complete a desired task, right. So the functions of this directional or direction valve itself, okay, is to control the directions of the pressurized air within the pneumatic installations, okay, pneumatic system installations, okay. So it's very straightforward, all right, just to control the behavior, all right, of the cylinder, whether to extrude or retract, right. Here is the common schematic, all right, I would say schematic, or yeah, schematic of pneumatic system, okay. This type of schematic is similar to the hydraulic, right. So if you can design for this, then hydraulic would be something similar, right. So you will see that the piston itself can be in this way, okay, and we represent this so-called piston, okay, into maybe just a cylinder, right. So we call it as a cylinder in the form of square when we draw the hydraulic, right. So this source of air will now comes in to push it forward, right, to push it forward, right. But when it is being blocked, right, so when it is being blocked, then we will use another symbol like a T, okay, because it's being terminated, so it's not connected to the other side. So when it can flow from one end to the other end, okay, so you can see that it flow in and out of that cylinder itself, okay. Whereas for this one is being blocked, right, so we have 2 TT, okay, at the cylinder. So when we combine this, okay, so this represent the functions of this piston itself, okay. So this piston itself, at certain point, it allows the air to flow from one port to the other, okay. At another state, okay, yeah, in another operating state or operation state, it will block the flow of the air, okay. So we have this block, right. So when we combine to describe the operation state of this cylinder, we just use these two blocks connected together, okay, so that it can switch, okay, from either this mode or the other mode, right. So this would be the source and that would be the outlet. It may be connected to another one or just released to the air, okay. So here is the simplified symbolic representations, okay, that would helps you to understand how it is being constructed according to a standard, right. So each of these rectangle will represent the position of a valve or a state itself, okay. So you may have 2 rectangle or 3 rectangle depending on the state that you can operate within that particular cylinder, right. So we can say that there is the number of switching positions that the valve have, right, that the valve has. And then inside the rectangle, now we would now draw the route of the flow, okay. It may come from one port to the other port, right. It may in the form of cross flow, because we may have maybe 4 ports, 2 in, 2 out, and so on, right. Then also we have this tau T, okay, as the isolations point to stop the flow of the pipe, okay. So if there is 1 in, 1 out, then we may need 2 T, right. If we have only 1 in, no out, then we have only 1 T, right. So all these point should connect to our external line. So you can see that outside the the rectangle, okay, we would have this external line. Okay, so this external line represent the connections to the pistons or the device itself. Okay, it represents how many ports that you have. All right, so in this case it is always 2 ports. Okay, it can become from one side or the others, right? Then how it would be operated, then we just use like previous one, we just combine with different state of block itself. Okay, so it can be initially closed, right? Or we, as we learned previously in the relay, we have normally closed or normally open. So in this way we would say is normally open. Okay, in the circuit it is not connected, right? When we do the switching, right, so this block will now switch or move positions. Okay, then it will allows it the flow to flow through it, right? Then others connections would be a triangle. So this triangle represent a free exhaust to the environment, right? So you may want to exhaust it direct to the environment, or if you have a line, that line represent a pipe. Okay, so you may connect to a pipe before it goes to an exhaust. Okay, so the triangle represent an exhaust. Okay, and whereas this circular with a dot represent the source of the pressurized air, right? Now we would now see a clearer picture of it. Okay, how we can represent an operations of pistons, okay, using these symbols, right? So these symbols represent, as we can see, 2 square, right? Meaning to say there is 2 state of operations. Okay, so these 2 state operations, now also we can see that in this piston there is 3 port, 1, 2 and 3, right? So we will say a 3 port and 2 state or 2 way of operations. Okay, so this piston we may later on we just write 3/2 and so on, right? So 3 port, 2 positions of switching. Okay, so for the first state of switching we can see that it comes, okay, remember this not as source, okay, and this represent the exhaust. Okay, so if we can see this 3 port, 1, 2 and the third one, okay, 1, 2 and the third one, in our system here we may always have this so-called fixed positions. Okay, it's only switching between the internal part of the cylinder, right? So now these 2 remain the same. Okay, only these 2 rectangle will switch, right? So this state will represent this part. Okay, and this another rectangle will represent this state or operations, right? So we just check the first one. So the first one will allow the flow of the pressurized air from point A, right, to the output port. Right, so it will go straight out. Okay, where at this side of the port it will block it. Right, so you have a T on this side, whereas on this state of operations you can see that the flow now coming back. Okay, because after you compress it, this single acting cylinders will now want to retract. If you still block it, then the air will not able to release, so you need to allow it to release to somewhere. So this valve will allows it to be released. Okay, after being pressed by this spring, right? So this will release at a different port. So now it will come back from this port to the port B. So you can see that this connection of port goes straight to the port B, right? So this is how it illustrate the operations of that valve itself, right? So this valve will operate in this way. Then also there is a 4 port. Okay, you can see 1, 2, 3, 4 ports. Okay, to control this is a double acting because we need two in and out. We need to control the switching of this, right? Then very straightforward, this go in, the other side go out. So go in, go out, right? So once it return back, if you want to switch the return of the directions of the pistons, okay, to retract, then we have to cross it, right? So when we do the crossing, then the operation is just to cross, okay? So this point cross to the other side, this one move cross to the exhaust, okay? So it's really represented by these symbols. Here are the common or the basic directional valve symbol that we usually use, okay? So as we have discussed, the front 2 represent the number of port, okay? So 2 represent the number of port, right? So you can see 1 2 3, this is a 3 port, right? This 4 means 1 2 3 4, you can see 2 out and 2 in maybe, right? Then this two-way, 3-way, and so on represent the number of switching or state of it, okay? So these 2 represent 2 cylinder, right? These 3 represent 3 cylinder, okay, and so on, right? So this is how you can visualize it and how it is being applied. So these are the common valve that we usually use, okay, and it can do us a wonder of controlling, right? Then also when we present this in our diagram, all this represent the normal or the initial positions, okay? So if we present in this way, meaning to say initially is always closed, okay? Or in this way, it means in the initial stage or normally it is open, right? So that is the idea behind it, right? So by that you should be able to interpret or read this kind of pneumatic diagram, okay, and understand the flow of it, right? Then when we come to the physical part, the contact part, then we may want to know how we actually activate that kind of valve, okay? So the easiest way of activations, the most conventional way of activations will be through the mechanical way, okay? It's either button, human press it, right? Or using a lever or pedal. So all this would be in the form of sort of like a limit switch, okay? You have a lever that when something go through it, okay, then you will push it, okay, and you will activate that or maybe release a certain valve, okay, or change the state of the valve itself, okay? So that would be in a way of mechanical actuations, okay? Pedal also you can use human foot, okay, to pedal and so on. So this would be in the manual control, okay, and the mechanical control of using sort of like a limit switch, a spring or toggles, okay, and so on. Whereas in a electro-pneumatic system, then we may also include what we call as electrical actuations, okay, by adding a solenoid, okay? So this is a symbol of a solenoid, okay? Then this solenoid may have a return spring or maybe both sides are solenoids. So how to know which one is being activated is you see this this square, this square itself, okay, it's connected to this solenoid, all right? Meaning to say when this solenoid is being energized, this state will be activated, okay? Means this will move over here, right? This is the how we can read the position of the solenoid. Whereas for this one, okay, means since we have these two, then they may label this is a solenoid 1, solenoid 2, right? Or okay, so if we activate solenoid 2, then this one will be activated, which is connected to next to it, okay? Whereas if we activate this solenoid 1, then this state will be activated. This is how we read it, right? Now after that, based on that concept, we would be able now to further interpret the operations of this pneumatic diagram, okay, by the operations of the directional valve, okay. So this kind of symbolic, it will be very useful for us so that we don't need to draw the whole, how we say, the whole logic, okay, or the whole device itself of the valve, okay. It's much easier to read, right? And this would be when it's non-energized, the solid non-energized, and this is where it is being energized, as I mentioned previously, right? So when this is connected to this side, so when it energizes this solenoid, this part will be activated, or this state of operation will be activated. Same thing for three-way, okay. So then you will have two solenoid, okay. Then how would this operate? They may have normally open, okay, when non-energized is in this way, okay, because there is a spring over here, okay. It will always go back to the non-energized state, okay, because of the acting of the spring itself, okay. Now when we energize the correct solenoid, then it will activate the correct state of it. Come to the applications now, then we will see it can be utilized, okay, in different form, okay. This represent a simple ideas, okay, of how we can visualize this automatic tank filling, right? So this automatic tank filling using a pneumatic circuit, okay, where we have a mechanical float, right? So this float, when the things goes up, then you will start to touch this sort of like a limit toggle, okay, limit toggle. Then when it is being touched, then this valve will now switch positions, right? So when it switch positions, then the pressurized air will not able to operate this part, okay. So if it is not touched, then the pneumatic air will continue to activate this particular valve, and this particular valve will actually allows the fluid to flow, right? So you can see that this would be a common symbolic to represent most of the fluid, okay, not necessarily a pneumatic, but also water and other things, okay. So it's very straightforward to see. There are also what we call activations of a valve by another valve, okay. So this is the idea of activations of this valve, okay, which is exactly the same valve of this, but only with a button, right? So why we need using the same two valve, okay, exactly the same, right? Only difference is this one is the manual push button, okay. Then this valve is activated through pressure, okay. So you have a pressure signal, okay. So the idea is that sometimes you may want to operate multiple cylinder, right? So by pressing one, then it can control multiple valve, or you may also want to use this piston cylinder may have a different requirement of how would say power, right, or pressure, right? So because of that, the selections of the valve may be different, okay. The sizing of the valve is different. That's why this may be too large and not visually good for you to manually operate using hand, okay. So you may want to remotely operate it through another valve of it, alright. So this is the idea behind using one of the valve to activate the second valve, right? So this is a way of using fluid power to control, okay, instead of the purely electrical signal of control, right? So in the electro-pneumatic automations, okay, then first part we have cover mainly on the pneumatic operations diagram, okay. You should be able to visualize this one, right? The movement of this, okay, with a limit switch, okay, and the valve, right? Then after this, then we would want to design or to illustrate how this pneumatic system should operate in electrical automations. Okay, so this automation circuit looks like I would say similar to a ladder diagram, some quite similar to a ladder diagram, right? That you may learn later on. Okay, so it's very straightforward. There is two line. Okay, this single line is one is neutral line and one is your rated voltage or current, right? So we have the R. Okay, so this is how we activate the circuit, right? So in this automation circuit, there is one set of line and there is another set of line. Okay, meaning to say this one would be like a control of the relay and this one would be the control of the valve, right? Sort of like this. Okay, but both must be connected to the power, right? That's why it's connected to these two RN line, right? Okay, here there is a limit switch, okay, being represented here, and then there is a stop button. Okay, means if in emergency or what, you may want to press the stop button. Okay, so normally this stop button, you can see normally it is closing the circuit. Okay, and also same thing with the limit switch, normally it closes the circuit. All right, so normally these two things not touching and the limit switch without touching and the stop button is at the normal positions, it will operate. Okay, but then there is a start button. This start button always open, right? And this is representing of a normally open relay. Okay, relay D, right? Okay, normally open relay. Okay, so to operate this relay, we must need to activate this relay in order for us to close this. Okay, so before we can activate this relay, we must press the start, right, to activate it. So to operate this circuit, okay, you must first press the start button, so it will now energize this relay and change the state. So once this relay change the state, so it will change this state and change this state, right? Both of this. Okay, this is just a symbol, not, all right, just you have to remember this is a symbol of the relay being operated by this, right? It's the switching of it. So once this switch, now no matter you release the start button or not, okay, the operation will now start to move. Okay, because of this part. Once you switch this relay, this is what you now start to change state to close, right? So the flow will go like this, right? And this part will just continue to operate this. Okay, so it will keep energize this part, right, to push until it reach the limit switch. Once it reach limit switch, this circuit will break, right? Once it's break, then this one will now switch off and this one back to the normally open side. Okay, then it will switch off, right? Once it switch off, then this solenoid will come back to this part. Okay, and allows the piston to retract back, right? This is the idea of how you can read the automation circuit together with the pneumatics diagram. These are the common symbols of switching contact. Okay, as you can see, this is the contactors, right? And then these are the positions of the normally open or normally closed. It can be a contact relay, it can be a buttons, limit switch, right? Or you may want to have the like a SPDT and so on of kind of switching, right? Then also you have the solenoid valve control type. Okay, and the letters that we used previously, remember the D is an auxiliary type of relay, means it's far away, sort of far away, that is used to do the switching, right? It's not the main power relay that power the whole operations, right? It's just to use for to control the input or the output of a certain operations, right? Then we go through another examples of electro-pneumatic automations. Okay, so again, because it's electro, then there is a automation circuit. Okay, maybe in the form of electrical later on, right? So this is a lightweight elevator, okay, to elevate the object to a certain positions, okay, that you want through the operations of a pistons, right? So you may have the flow control valve, okay, and the directional control valve itself, okay. So you have the solenoid A and B, right? So normally they are open, right? So no flow is flowing until you activate whether you want it to go. If we activate solenoid A, okay, then it will go in and push this side going up. So meaning activate solenoid A, it will goes up. Activate solenoid B, it will goes down, right? Okay, so same methods, okay. And when you originally nothing is on, okay, because everything is normally open until you press the start button, then you will start to activate this relay, right? So this contact relay. So you can see that most of the time this button we have this part, okay, to skip it, okay. The idea of this is that so that you can press one, okay, if you continue to operate, right, until you press the stop button or certain, yeah, in this case when you press the stop button. Otherwise you may need like the previous one, you add a limit switch, okay. When it reach certain level, it will break or stop the operations, okay. So this is how you can design it, right? So this relay now, auxiliary relay now will operate this whole idea, right? So once you press the start, it may not start immediately. It only tells the machine the machines to be ready to start, okay. Now in order to control the directions, whether it should go up or down, then you need to again press the desired button. If you press up, right, so it will allows it to go up, and you can see that this is normally closed, okay. Two line with a straight through, so-called a line in between them, this is normally close a symbol. So it will normally close, right? And this will be controlled by this D2, right? So normally they are closed, right? So first thing, when you press up, okay, then you will activate D2. What it means by D2 is that now when this activate D2, it will first make sure that this circuit will not be activated. So it will now open this up, right? So this down will not be able to operate, right, until you disconnect this up button, right? So it's just a safety part, right? Then second part would be now it will operate this D, okay, so that it will operate or energize the solenoid A, right? Then if you want to make it downwards, okay, either you press the stop button, so it will stop everything, right, reset everything to the original state, or you have to disconnect this one and press the down button. Now again, once you press the down button, then this is normally closed, and you will again make sure the up will not operate, right? You will disconnect that part and operate the rest, right? So this is the idea, the safety behind it. Another examples or when you design the electro-pneumatic automations, one of important or maybe useful diagram would be this position step diagram, okay. You may want to sometimes visualize how the operations of the cylinders, maybe multiple cylinders, maybe you have cylinder 1, A, B, C, and so on, okay. At certain state or step or time, okay, you may want it to be at which state, okay. So this this diagram will help you to visualize, okay, whether it should be at position 1 or position 2, right? So this would be very useful for you to visualize the whole operations when we involve multiple cylinders, okay. So how to read this one? Again, position 1, okay, both are down, okay. So when it reach position 2, then this one now should slowly go up. The cylinder, no, wait, okay, position 1, okay, so this one go up, okay, but cylinder B go down, go in, okay, alright, okay. Then after that, cylinder B will go to the state number 3, then it will push, then it will go down. At state number 3 it will come back again, then yeah, go down again, right? So the putting of this may be, you start it already, okay. So this object will immediately come to here, okay, before we activate. So this one, after it reach here, then it will start to slowly go up to position number 2, right? So this is the idea of the diagram, right? So same thing with another example. This is automation to separate a similar ball, right? So you can see that there is a piston just to separate the ball, okay. And here we use a proximity switch, right, to detect whether the ball size or maybe the passing of the ball through the gravity, right? So this will switch, okay, to different positions, right? So the ideas remain the same, okay. You have this bypass, so-called bypass relay, okay, to make sure that it will still continue to operate after you press the start button and you release it, okay. Same thing for this part, okay, this C itself, okay. So now after it activates this circuit, you can see that this PS2 is always open, okay. PS2 is always open, as we can see, but PS1 is always closed, right? So meaning to say, most of the time, okay, at first it will just go through here, right? Normally close, and you will activate this one, okay. So you will just pump, and this one retract here, right? So pump and retract. So most of the time, original or initial rest position, this piston will be inside, okay, until you start to activate this P2. So when there is a ball passing through and it detects, okay, then you start to switch this close, and then this one will now switch this on to operate. So once it switch on, then if there is another ball passing here, then this one will again open up, okay. So once this passing through, okay, you will activate continuously and release. So this one will now moving to the other side and push another ball over here. So when it passes through here, then this one will deactivate, so it will retract again, go back, okay, and so on. So this is the idea of this circuit. We have another circuit, all right, that operates, okay, involving cylinder A and B. So again, as we can see, when we involve more than one cylinder, and also cylinder C, then this displacement step diagram will be useful for us to visualize, okay, when it should be activated, okay. And then in this automation circuit also, we can see that it is connected, and it is also connected to the second line of it, right? So this is how we can visualize, okay, and check, right? So this is a stamping machines, okay, and when you press start, okay, unless you press the stop button, it will continue to operate, okay, because it's now contacting through it, right, to operate the other segment, right, of cylinder A yeah, cylinder A, the cylinder B, and the cylinder C, or the coil C itself, right? So this is how you can operate multiple cylinder and activate when it is required.